lecture? Huh? Yeah. It's typical futurists. There's a whole group of futurists that some of it will probably be right. You know, I mean, look at the futurists who were making Star Trek and stuff. You know, they had those things look a lot like cell phones. You know, laptops. All that stuff wasn't around, but when they were making those movies, a lot of those things did come into play. Some of them didn't, you know. But all right, it was pretty cool. The next person to come is Hillary Clinton. So I don't know if they'll offer us tickets for that. I want a ticket myself because, but that's gonna be a tough one to come by. We'll see. All right, so your test, okay? You'll have on your test, which is tomorrow, right? Oh, I want to start recording this for GE block. Oh, it is recording. Your test is these aren't in any particular order. I just put one type of problem on there. One type of problem is going to be on like modeling. And in that case, I know we talked a lot about how models evolve, and we made up our own model for the light bulb and the demo like that. But this will be one of the ones that we did, the mathematical modeling, a linear model, right? Where you have to find the slope and the y-intercept, and you have to have appropriate labels for y, appropriate labels for x, and units for all those things. And I might have you take your model and extrapolate it like we did in the lab, the not lab. Okay? Maybe interpolate it, maybe extrapolate it. I might have you explain what those terms mean. Okay? Then another type of problem that we did was conversions. Okay? So you should expect something like changing miles per hour to standard meters per second, something like that. But also one that might take like changing a density of grams per cubic centimeter to kilograms per meter cubed, something a little more expanded with the squared or the cube in it. You remember when it's squared or cube, you got to do it multiple times. Yes. Yeah, you'll have a reference table. Okay. That table you have, you'll have on all tests and all exams. Okay. Then the third type of problem will be finding x and y components of a vector. Okay? And the third or the fourth type of problem is graphical addition of vectors. Scale, protractor, things like that. You can use your protractor too, but I'll have protractors and rulers for you if you want to use those, okay? And then the fifth problem is the mathematical addition of vectors. So in the graphical one, you have a scale, you have a ruler and a protractor, and you go in the direction based on the angle and based on the length of it. You measure it and you put it there, and then you put the next one head to tail, right? And you put that on there. and then the sum is from where you started to where you ended. And then you can measure that, and you can convert it using your scale. You can convert it to whatever unit it is, kilometers or something like that, and then you could find its angle from the protractor, right? In the mathematical addition, there were multiple steps to it. So if we had three vectors we were adding, the first step was to do what? Draw them, okay, rough sketches. They don't have to be exact. Okay, hold on. I hear two people. Kendra? Well, you're too far ahead. You're way too far ahead. That's what we're going to do, yes, but before we do that, Maya? Okay, for each vector, we find the x and y components, right? And then we add the x components of all of them together. We have a new sum of the x components. We add all the y components together. We have a new sum of the y components. Those are at right angles to each other. Then, from here to here, right, that's the resultant, which is also the hypotenuse of a right triangle. So we use Pythagorean to find the resultant, right? How do we get the angle? Tan inverse of y over x. And then we've got it. Let's do some problems like that. I think I have a linear one here, but I feel like you guys are better at that than it would be better at looking at a conversion one, okay? Let's just take a squared one, like 90. Let's say you just bought a new tract of land, okay? Uncle Fred passed away and left you a large tract of forest at 90 miles squared an area, okay? Now you want to convert that to meters, so how would we go about doing that? Well, the first step would be to go to your reference table and to look at on there and see if there's anything that relates miles to meters, okay? Now some people, it helps because if you get miles squared, you know, you could write miles up here and remind yourself that you have to do two conversions for each of those. I look on there, it says 1609 meters in 1 mile. So I know I have to go meters, meters. So that's sort of my plan of action, okay? Miles, miles to meters, meters. And then I do the conversion factor. I'm going to need two of these. And you can see, that's what we call them, two Homer Simpson eyeballs, right? If you see that, I don't know. And where does miles go? Up here? Why on the bottom? It has to cross out. We're going to have two of those to cross out. Miles squared is miles times miles, right? And then I look at my conversion. That's going to tell me where to put the 1609 and stuff. Okay, so 1609 meters, 1 mile, 1609 meters in 1 mile. And then you could just ask your calculator to convert it for you in the future. Celsius, right? Find 90. What is 90 miles squared in meters squared? Now I still have to punch it in, but do you get that joke? Like serious, right? But since it's a math, science, we call it Celsius. Isn't that funny? Okay. 232,999,290 meters squared. So when you're at the funeral, you could say, "Thank you, Uncle Fred, for the 232,999,290 meters squared of land you left me, right? So, all right. Now this written out in scientific notation, that would be 3, 6, 7, 8. 10 to the 8 meters squared. Yes. What? Did I forget something? Oh, I forgot the 9. This, oh, right here? Yeah, that could drop off. There we go. If written out would say that all those are significant, which it would be significant if this was an exact number, 90 miles squared. I doubt it is, though. Probably just a survey, right? So, okay, that's conversions. Let's look at finding vector components. Well, that shouldn't be too hard, except to take into account direction, okay? So let's say we had a vector that looked like this, okay, down here, and you were given this angle that goes across, and the angle was 100 and, no, I'm sorry, it has to be bigger than that, 200, well, let's just say 200 degrees, okay, like that. And your thing is find the x and y components. Yes, you're right, we do. And I'll give you that. Let's just say it was 55 meters. Okay? Better? Yes. No. No. It doesn't. At this point, no. No. I don't care. I can figure both out. But we will work with more scientific numbers later, scientific notation, especially when we start talking about things with very small, 10 to the minus 11. Gets annoying to write 10 zeros all the time. And or other things like 10 to the 26, stuff like that. That gets a little annoying to write a bunch of zeros. So, okay, so on this one, how do we go? Well, let's see. Let's have who could come up here and draw the x component? Spencer? Just put your finger on the board and draw it. It should be all set up. Well, okay. Hold on. Put your finger on the board and hold it on the board. And draw it. Good. Now, who wants to draw the y component? Vera? Good job. Both of you. Great. Now, the x component, you can use in your component formulas this theta from the x-axis of 200, and what it will give you is a negative x and a negative y. So it will know that 200 brings you into the third quadrant where both x and y are both negative, right? Okay. So, but you could also use the, what we could call like a theta prime if you wanted to. And theta prime here would be 40 degrees because 180 brings us to here. Oh, did I say 200? I meant, so it's 20 degrees, even though obviously it's not, but that's okay. It's 20 degrees, sorry. It would be our theta prime, right? Just meaning like the small theta that goes right to the x-axis, okay? But still, with the component formulas, you could put in the components right into the formula. Who remembers what the component formula was? Let's just call this R, this vector R. What's the component formula for x? Yeah? Right. What's that? X is cosine, that's right. So cosine is adjacent over hypotenuse. So it comes out like this. Rx, which is this one, equals R cosine theta. That's right on your formula sheet. Okay? Ry is R sine theta. Okay? So, then it's just putting them in. 55 meters, cosine of 200 degrees, and Ry would be 55 meters, sine of 200 degrees. Now the problem comes in for a lot of you is your calculator. It should be in degrees, and so if you have your calculator, get it out so to make sure if you make a mistake, well, now it's the last time to really catch it and get some help with it. But for me on this calculator, which I don't really like, because I know you have to hit 200 and then you have to hit cosine, and it's in radians. No, it isn't. It's negative because it's in that quadrant. Okay, fine. Times 55. Like, all right, we'll round it to the 10th. 0.7, right? That's your Rx. If you don't get that, raise your hand. How did we get to 20 degrees? That's a good question, right? Who could tell Mary how we got 20 degrees? Kayla? So this is 180. So that's 20. But you don't really need it here to get this. So this whole angle's 200. So if this is 180, what's left? 20. Got it? Okay, and Ry was what? To the 10th. Negative 18.8 meters. And you have your x and y components. Okay? Yeah. I think that should be fine, unless I state something differently. Everybody got that? Well, if you use 20 degrees, it would be positive, but then you would know to interpret it and write it down as negative. You see what I'm saying? Yeah. So, but either way is okay. It's always a good idea to draw these things too. So if you're given one that says find the components of a 55 meter vector at 200 degrees from the x-axis, the first step is to draw a rough sketch of it so you know what components are. You know what I mean? So that, yeah. So that this is a very important part in physics is the sketch that goes into it and to go forward. And when we get into forces, do force diagrams, okay? And those will play an important role in figuring the problem out. If you don't have that, for me, a lot of, even like a car accelerating, I'm always drawing like the car, right? And it goes a certain distance, right? Okay? And it has an initial velocity. And it ends up at some other velocity over here. Oops. Of, 20 meters. Stuff like that, so that it's on there and I know it's part of the problem. Now that, you don't need to know that right now, right? But okay. How about, let's skip to, we did a lot of the graphical ones, but let's go to the mathematical adding of vectors. So let's say you had a 20 meter vector at 30 degrees, okay? We want to find the sum, call it R, of A plus B plus C, okay? We have A. Well, I haven't drawn them yet. A is that, 20 meters. B is also 20 meters, but it's at 90 degrees. And C is 20 degrees, and it is 35 meters. We have three vectors, okay? What's the first step? Spencer said draw them. We did that. What's the next step? Julia? X and Y components of each. So I'm going to find this, my AX. I'm going to find this, my AY. I only have a BY. No BX, so BX is 0. I'm going to find my CX and my CY. And these are the same way that we just found the other components. So AX equals 20 meters cosine of 30 degrees. Which would be 17.3 meters. AY would be 20 meters sine of 30 degrees. Oh, that's an easy one, isn't it? 10 meters. Of course, you're learning that with your mathematician teacher, right? No? You haven't used sine, cosine? Yeah, you have. Thought so. So we have those two. Now A or B, BY is all we have. Let's put it down here with the Y's. And BY is just 20 meters. If you wanted to put in sine of 90, what would you, oh wait, no. AY would be, yeah, sine of 90. What's the sine of 90? 1. Huh? Right? Cosine of 90 is 0. Sine of 90 is 1, so it's just equal to that component. And then CX is 35 meters cosine of 20 degrees. 32.9 meters. And CY is 35 meters sine of 20 degrees, which is, I fell behind, 1.97? 11.97. Or how about just 12.0 meters? Don't forget your units, Aiden. Like on your packet, you forgot your units. Exactly. So, say it again, Vera. What do we got to do next? Okay. So, our RX,